and get started. So today I'm just going to go over all of section 5, which will be on your final exam, as well as section 4. If we have time, I might go through like a few things in section 4 if you guys want, if we do have time, if you need a refresher on that. But this will be mostly focused on section 5, which is nucleophilic substitution. So I'm going to go over just the basics of those reactions. SN1 reactions and SN2 reactions, the factors that determine which of the two mechanisms, the elimination, side reactions, benzylic and allylic substrates, ether synthesis, and esterification. So first is just the basics of nucleophilic substitution. So if you remember, a substitution reaction is just when a functional group of an organic compound is replaced with another functional group. And in this case, the attacking agent is a nucleophile. And you'll start with 2 products, end up with 2 products, except in the SN1 case, but we'll get to that. And if you remember, a nucleophile, it's an electron pair donor. So it's electron rich. It can donate an electron pair. And then we also have an electrophile, which can accept an electron pair. And nucleophilic substitution can happen via 2 pathways, so either SN1 or SN2. And down here is the general equation for those. So you'll have a nucleophile, which has a pair of electrons that it can donate, and then your substrate, which has this electrophilic carbon, and also has a leaving group. And a leaving group, the only ones you'll probably see are either water, so H2O, or halogens like chlorine, bromine, iodine. And a general product is you'll replace your leaving group with your nucleophile, and then your leaving group will come off. So substrates can be classified as methyl primary, secondary, or tertiary, and that will determine whether it's SN1 or SN2. And the substrates have to have a sp3 hybridized carbon. Okay, so we can have either SN1 reactions or SN2. So SN1 reactions happen in 2 steps. So the first step, the leaving group comes off and a carbocation is formed. And then the next step, the nucleophile comes in and attacks. So there's 2 separate steps. The rate of SN1 reactions, it's a first order reaction. So it's equal to your rate constant times the concentration of your substrate. So it's a first order reaction, hence SN1, which means that only one compound is involved in the rate determining step, which is going to be the formation of your carbocation. And that's the slow step as well. So, and if your substrate is chiral in SN1 reactions, your product will be a racemic mixture, which say if your substrate is in S configuration, then a racemic mixture is an even mix of both S and R configuration. Okay, so you'll have 50-50 S and R. Okay. So I have a few examples of SN1 reactions here. If I could see it, I'll redraw this. Okay, I think this is what I had. Okay, so this is a Lucas reaction, if you'll remember that. So what I always normally do is I'll go through and label my substrates to classify them as primary, secondary, tertiary. So this alcohol right here, this OH group is going to be my leaving group once I protonate it. And this is connected to this carbon here, but it's connected to 3 other carbons. So this is a tertiary substrate. And this chlorine anion, this will be my nucleophile. Okay. So I'll erase this. And we'll go through the mechanism. Okay. So in the mechanism, if you remember this, the first step is to protonate this OH group so it can become a good leaving group. So these lone pair of electrons from oxygen, you're going to take this hydrogen from HCl. This bond will break, and those bonding electrons will go to the chlorine. Okay. So I form H2O here, which is now a good leaving group, so this can come off. And this step is not involved in this is not part of the SN1 mechanism. This is just a step to get to a good leaving group. So this is where the actual SN1 mechanism starts. So the first step is your leaving group comes off. So this carbon-oxygen bond breaks. Those bonding electrons will go to that positively charged oxygen. You'll lose water. And then you form a carbocation here. Okay? And SN1 reactions always have a carbocation formed as an intermediate. So in this step, I formed a chlorine anion, so that will come back. And this is my nucleophile, which will attack, right, Carol, yes. So this chlorine anion will attack this positively charged carbon, and I'll form product. Okay, and I also formed water in this step here. Does that make sense? Okay, and you can tell this is an SN1 reaction because we have a carbocation formed. Okay.
You lost the water like on the third step, and then you got it back.
So so in this step, this water came off, and it's just a byproduct. I just rewrote it here.
Okay.
So that's actually formed in this step here, but it's still just a byproduct. Does that make sense?
Mm-hmm.
So I have another example down here. What's the mechanism for this? So again, your first step in SN1 mechanism is your leaving group comes off first completely. Okay, so this carbon-bromine bond will break. Those bonding electrons will go to that bromine. Okay, and you form a carbocation. And you lost bromine here. Okay, so then where I lost this bromine here, this anion, or no, that doesn't come in here now. Sorry. So my nucleophile in this reaction is water, actually. My bad. Okay, so water is nucleophilic because these two lone pairs of electrons on oxygen. So I have a carbocation formed. These lone pair of electrons from water will come and attack this positively charged carbon. Okay, and then one of these hydrogens will come off because this oxygen is unstable, which will form, I'm going to put it up here. Sorry, this is messy. This will be our product. So from that last step to this one, we took one hydrogen off this water here because that oxygen was unstable, which formed our product here. And then you also form a byproduct of HBr because this extra hydrogen will bond with that bromine. You following me? Yeah, because it has that positive charge, so there's too many bonds. So one of those hydrogens comes off very easily to make it stable. I'm sorry, that's so messy. Any other questions on that one? Okay. So our next option is SN2 reactions. So SN2 reactions happen in one step rather than two. So in SN2 reactions, the leaving group comes off and the nucleophile attacks from the opposite side at the same time. So it only happens in one step. And the rate of SN2 reactions is your rate constant times the concentration of the nucleophile times the concentration of your substrate. So it's a second order reaction, hence SN2, which means that two compounds are involved in the rate determining step rather than one in SN1 reactions. So in SN2 reactions, if your substrate is chiral, then if you start with S configuration, then your product will be an R because your nucleophile is attacking from the opposite side. So it'll switch the configuration. Okay, so here are some examples of those to go through. So in this case, I have a primary substrate, and then hydroxide will be our nucleophile, which is strong nucleophile. Okay. So let me rewrite this actually. Okay, so in SN2 mechanisms, your leaving group will come off, and then your nucleophile will attack at the same time from the opposite side. And this all happens in one step. Okay, and this bromine will actually combine with that sodium up here. But these are just, sodium is just a spectator ion, so you don't necessarily have to write that, because I'm just show that hydroxide is your nucleophile. Does that one make sense? Okay. So down here, we have an alkoxide here, if you remember those. And then a secondary substrate here. And it's a strong nucleophile. Okay, so again, my leaving group will come off, and at the same time, the nucleophile will attack at that carbon. Okay, and this is an ether, which we'll go over that more in a second, but this is an example of ether synthesis. So just the only difference here from SN1 is that it happens in one step instead of two. Does that make sense? Okay. So what determines if it's SN1 or SN2 is your main factor is your substrate, the nature of your substrate. SN1 reactions can only happen with tertiary or secondary substrates because you form a carbocation. And if you remember, tertiary carbocations are more stable than secondary, which are more stable than primary. So primary and methyl carbocations cannot actually be formed, so they cannot have SN1 reactions. But tertiary and secondary carbocations can actually be formed, so they can have SN1 reactions. For SN2 reactions, you can only have secondary, primary, or methyl, and you can have a tertiary substrate in SN2 reactions because of steric hindrance. So because the leaving group is coming off at the same time as the nucleophile is attacking, if there's three separate groups on that carbon, it gets really busy, and you have steric hindrance, and the nucleophile can't get in there effectively, or favorably, at least. Okay, so SN2 reactions It only happens with secondary, primary, or methyl substrates. So in SN1 reactions, you can use a weak nucleophile. Because you make a carbocation, you make a strong electrophile. So you can use a weak nucleophile. But in SN2 reactions, you do not make a carbocation, so you only have a weak electrophile. So you need a strong nucleophile. Okay, and your solvent. For SN1 reactions, it favors protic solvents, which are water and alcohol. Whichever solvents which can be hydrogen bond donors are protic solvents. And then SN2 reactions favor aprotic solvents, which can be DMSO, diethyl ether, acetone, or THF. And remember, this is DMSO, dimethyl sulfoxide. You'll want to remember that. And you know diethyl ether. And I hope you know acetone by now. Everyone good on that? Have any questions? Okay. So, and like in these last examples, we have a primary substrate, secondary here. So this secondary could have either SN1 or SN2, but because we have a strong nucleophile, we can have SN2 reactions. And this one is primary, so it can only have SN2. And we also have a strong nucleophile, that hydroxide. And in the ones before, this is tertiary, so you can only have SN1. And the same thing here, it's tertiary, so you can only have SN1. Okay, so something you'll want to look out for in SN1 reactions is elimination. So when you use a strong base in an SN1 reaction, you risk having an elimination reaction occur, which you don't want. So basically to fix this, just avoid using strong bases in SN1 reactions. Since you can use weak nucleophiles, use them. So we have an example right here. So if you have this substrate, it's tertiary substrate with hydroxide, which is a strong base, strong nucleophile. So this would be the product that you want if you're trying to do an SN1 reaction. But you can also form this as an elimination byproduct. So the mechanism, your leaving group will come off, your form a carbocation, and what you would want to happen is your hydroxide attack that positively charged carbon, and you form an alcohol. But what could happen is it attacks an adjacent hydrogen, and then those bonding electrons go and form a double bond, which you do not want to happen. You remember this kind of thing from dehydration of alcohols? It's the same kind of thing. That's what would happen, which you want to avoid that until next semester. So just avoid using strong bases in SN1 reactions. Okay, so benzylic and allylic substrates are a bit different. Even if both of these are primary substrates, they can still have SN1 reactions because they have double bonds here, which create resonance stability. Okay, so here's some examples here. So in this case, I have this benzylic substrate. I have a benzene ring here. I'm going to have this carbon here. So this is a primary substrate because this leaving group is connected to this carbon, which is connected to one other carbon. Okay, so you would think that it wouldn't be able to have SN1 reactions, but what happens is the chlorine comes off, you form a carbocation with a positive charge on this carbon here. Okay, and this carbocation is stabilized because of this ring. So this positive charge can actually delocalize to the ring, and it switches between resonance structures. So it stabilizes the carbocation and allows it to actually be formed because of those double bonds and those pi electrons. Does that make sense? Okay. And same thing with allylic. This is your allyl group here. So same thing, you could form a carbocation with the positive charge on this carbon. And again, you would think it wouldn't be able to actually be formed, but because of this double bond here, this positive charge can again delocalize, and it'll be stabilized by those pi electrons, and it'll switch between two resonance structures. Have any questions about that?
So on the silicon,
Mm-hmm.
how did you get OH and then outside of it?
Yeah, so that's the same thing from the other one. I just didn't write it out completely. So the water adds like this. It does add as H2O, but a positive charge forms on that oxygen because it has too many bonds. So one of these hydrogens will come off just spontaneously. You don't have to do anything, it'll just come off. Okay, so that's where you get that step. And same thing here, is the oxygen is unstable because it has too many bonds. Any other questions on those? Okay. So another example of SN1, SN2 reactions is ether synthesis. I had one. So ethers can be synthesized from an alkyl halide and an alkoxide or an alcohol, depending on what pathway, SN1 or SN2. So an example of SN1, here we have a tertiary substrate. So this leaving group here is connected to this carbon, which has 3 other carbons connected to it. So this is tertiary. And then this alcohol, which is a weak nucleophile. And my solvent is again ethanol, which is a protic solvent, which favors SN1. So I would get in the habit of, when you do these problems, to just classify your substrate, figure out if your nucleophile is weak or strong, and then figure out if your solvent is protic or aprotic, and then go from there. And I would label those. That's what I always used to do. So, mechanism. This is about to be messy. So your first step is your leaving group comes off, that carbon-chlorine bond breaks, and those bonding electrons go to that chlorine.
What's under the arrow?
It's minus Cl, sorry. Okay, so you form a carbocation here. And then your nucleophile, this is alcohol. I have 2 lone pairs of electrons on that oxygen. Okay, so this oxygen, those lone pairs will attack that positively charged carbon. I'll form a product. And same thing here. If I just added this whole alcohol to this, then this oxygen would have 3 bonds, so it'd be unstable, so this hydrogen will come off. And that hydrogen bonds with the chlorine from earlier. And this would be my product via SN1. We okay with that? Okay, this is an ether, by the way, if you don't remember. It's just an oxygen with 2 alkyl groups on either side. Okay, so I also have an example of SN2, because you could form ethers via SN1 or SN2, depending on the nature of your substrate and your nucleophile. So in this case, this is a methyl substrate, okay, because this carbon is connected to no other carbon, so it's just a methyl carbon. And then this is a strong nucleophile because I have that full negative charge on that oxygen. And this is an alkoxide. Remember that. And I'm using DMSO, which is aprotic. Okay, so all of those favor SN2. Okay, so my leaving group will come off, and at the same time, the nucleophile will attack this carbon. The carbon, not the hydrogen. Okay. And then I'll form a product. This bromine will come off and combine with this sodium up here. And this will be your byproduct. Does that make sense? Okay. Any questions so far about this? Okay. So, last thing, esterification. So esters can be formed from a carboxylic acid and an alcohol. So this mechanism is kind of tricky, but stay with me. It'll be okay. So for esterification, you have to do esterification, or this is Fischer esterification specifically. You have to do Fischer esterification with an acid catalyst. Okay? And that acid catalyst is used to protonate this carboxylic acid. Okay, so this oxygen up here has 2 lone pairs of electrons. We'll come and take this hydrogen. Okay, and I did this because this carboxylic acid here, this carbon is weakly electrophilic. Okay, but if I'm using an alcohol, that's a weak nucleophile, and a weak electrophile and a weak nucleophile don't do anything. You have to have a strong of either one. So I made a strong electrophile because I protonated this oxygen up here. So this positive charge will pull electron density towards that oxygen, which will form a bigger positive charge on that carbon. So that enhances the electrophilicity. Does that make sense? Okay. So now I can add my alcohol. Okay, so this oxygen has 2 lone pairs of electrons. It will come and attach at the bottom of this carbon here. And at the same time, this double bond will break, and those electrons will go to that positively charged oxygen. Okay. So now this oxygen down here is positively charged, so there's 1 too many bonds. So what's going to happen called intramolecular hydrogen transfer or something like that. So this hydrogen is going to transfer to this oxygen within the molecule. Okay, so I just moved this hydrogen to this oxygen here. So I form OH2, so H2O. I formed a good leaving group. So what happens now is I still have 2 lone pairs of electrons on this oxygen up here. These will come down to reform a double bond, and which will push this off. Okay, so what I did is this whole group came off, this came up, and these bonding electrons here came down and reformed a double bond. Okay, so now this oxygen has a positive charge, so this hydrogen here will just come off. Okay, I know this is complicated. If you need me to do it again, I can. Okay, so then you form your ester here. Which an ester, so you have an alkyl group with a carbon double bonded to an oxygen, to another oxygen, to another alkyl group. Okay. You want me to do that again?
So how do you know that the oxygen has too many bonds?
So oxygen is bivalent, which means it only needs 2 bonds to be stable. Because look at the groups up here. Oxygen, it only needs 2 bonds to get to 8. Okay, so you just have to remember that oxygen is bivalent, so it's stable with 2 bonds.
So it becomes bivalent in the hydrogen, and then that positive charge goes with it.
Yeah, so the oxygen no longer has a positive charge when you take that hydrogen off because it's stable with those 2 bonds. Any other questions about that? Okay. So that's all I have for section 5. If you don't have any more questions about that, if you want, I can go back and do a quick few things on section 4 if you want a refresher on that, or whatever you guys want. Or you can leave if you want to. That's fine. Okay. I'll do a few things.
Would you ever like access these slideshows?
Yeah, I'll send it out tonight, either tonight or tomorrow. Okay, so section 4 is stereochemistry.
These slideshows?
Yeah. She's recording.
Right, but I wanted to see if like the actual slides, like print them all.
I think the whole recording can be rewatched.
Right. I meant like the thing in the recording, like the slide.
Oh, yeah. That's
Yeah, a lot of them just like to have my slides so just like practice on them. So I normally send out my PowerPoints. Okay, so section 4 was stereochemistry. The big things you'll need to know about section 4 is absolute configuration, which is R and S, and then conformational analysis, which is a thing where it's eclipsed or staggered. If you're like looking at the molecule straight on, if it lines up, that's eclipsed. If it's like offset, it's staggered. And typically molecules are more stable in staggered conformation. Okay, so let's see. So say I have this chiral carbon, and chiral means that the carbon is connected to 4 different groups. This sp3 hybridized is connected to 4 different groups. And to be chiral means that its mirror image is non-superimposable. So You can tell the absolute configuration by assigning priorities to the groups. So you have hydrogen here, which will be your least priority because it's based on atomic number. Hydrogen has the least atomic number. Chlorine will be 1, so has the highest atomic number. And then you're stuck between 2, and you're comparing the first atom that's connected to the chiral carbon. You have 2 carbons here, so you have to go to the second set of atoms. This carbon has 3 hydrogens. This one has 2 hydrogens and a carbon. So this will be a higher priority than this. Okay. So your next step is to make sure the lowest priority group is in the back, and it is in this case. So then you can rotate. So from 1, 2, 3, we're going counterclockwise, which is S configuration. Coming back. Okay, you want me to do one where least priority isn't in the back, or you want me to? Okay. Okay. So. Okay, so to have this, again, your first step is going to be assign priorities. Hydrogen will again be 4. Have an oxygen here, which is higher than carbon. So this OH group will be 1. And then again, between a methyl group and an ethyl group, ethyl is higher priority than methyl. Okay, so your next step is to make sure your least priority group is in the back. And it's not right now, so I need to switch. So you just switch groups 1 and 4, because 1 is in the back right now, and I want 4 in the back. So we'll just switch 1 and 4. I really did not leave myself a lot of room here. It's okay. And when you switch groups, just be careful to keep all of your wedges and lines in the same place so you don't mess yourself up. Okay, same priorities. 2, 3. So now 4 is in the back, so now I can rotate. So from 1, 2, 3, going counterclockwise, which is S configuration. But because I've switched 2 groups, the original molecule is actually in the opposite configuration. Okay, so if it's S configuration, when I switch 2 groups, the original is in R. And if you need to switch groups, if you don't want to flip it back, if you switch 1 and 4, you can also switch 2 and 3, and it'll keep it in the original configuration if you want to do that, or you can just switch 2 and then flip it back. It's up to you. Any questions on that? Okay. If you don't have any other questions, then that's all I have, my friends.
Thank you.
You're welcome.